All right. Hello, everyone. Welcome to the seminar for today. So I'm delighted to introduce Joshua Benabou, who is tuning in from UC Berkeley, where he is a graduate student working in the group of Ben Safdie, and is doing a lot of very interesting work on axions and axion dark matter. And today he's going to tell us very excitingly what the mass of the QCD axion is. So thank you very much, Josh, for coming and giving us this virtual seminar, and I'll pass over to you. Thanks.
Thanks so much, Karen. Yeah, so it's my absolute pleasure to tell you guys a little bit about the QCD axion, and in particular, what we might expect for the mass of this particle. And what I'll try to argue is that this question is intimately related to, firstly, the cosmological history of our universe, and secondly, the UV completion that we assume for the axion. So my plan is to very quickly just review the strong CP problem, and then I'll talk about the post-inflationary cosmology that arises for field theoretic UV completions of the axion, and how in that scenario, in principle, we can make a prediction, a unique value that can be predicted for the mass of the QCD axion, assuming it's all of the dark matter of our universe. I'll then talk about string theoretic UV completions of the axion and how that leads to a different cosmology where we don't have a predictive scenario for the mass of the QCD axion, assuming it's the dark matter. And then I'll tie everything together by saying, telling you about some new work from last week about how in string theory, we can still make a statement about what the mass of the QCD axion is if we make an additional assumption about what the standard model does in the UV. In particular, if it unifies into a gut, we'll be able to place an upper bound on the mass. So I'm guessing that people are quite familiar with this with QCD axions in general. So I'll just go quickly through this part. So what are they? They're a hypothetical particle that was introduced to solve the strong CP problem of QCD, which is the question of why the electric dipole moment of the neutron is measured to be so small. So there's this term in the QCD Lagrangian expressed here in terms of the gluon field strength, G, and its Hodge dual, G tilde, and this dimensionless parameter, theta bar, which can be thought of as an angle between minus pi and pi. And this term violates CP generically when theta bar is not zero. And you can compute in Cauchy perturbation theory that this term induces an electric dipole moment for the neutron, which is proportional to theta bar. And people have gone out and measured that dipole moment. And what experiment tells us is that theta bar is consistent with 0 to 1 part in 10 to the 10. So that's the problem, right? You have this order 1, a priori order 1 number between minus pi and pi, which happens to be so small. And why is that? So the axion solution to this problem, which was developed by people like Wilczek and Weinberg and later Peccei and Quinn, is basically to promote theta bar from a parameter to a dynamical field such that you can dynamically relax the coefficient of GG tilde to 0. In more detail, we add some new field, A, the axion field, which couples to QCD via this dimension 5 operator, A, GG tilde. And now we have some new dimensionful scale in the denominator, Fa, which we call the decay constant of the axion. And you can work out in Cauchy perturbation theory that this field gets a potential from strong dynamics. And the minimum of that potential is precisely where this term in parentheses is 0. So if theta bar is non-zero, the axion just relaxes to the value necessary to cancel this coefficient of GG tilde and remove the CP violation from this QCD Lagrangian. So a very elegant solution. And what does it tell us about this, this new field? Well, as I just said, it gets a potential from QCD, and so it has a mass. An approximation to that potential is this cosine potential here. I've allowed for some periodicity of that potential through this integer number inside the cosine, this n domain wall number. And importantly, this potential is proportional to the square of the mass and the square of the decay constant. Now, as I'll discuss later, this potential will be dependent on temperature, since QCD in the early universe is at finite temperature. But at 0 temperature, you can compute in Cauchy perturbation theory what the mass is in relation to Fa, and you find that they're inversely proportional. And so for Fa, it's something like 10 to the 12 GeV. You're talking about an ultralight particle with a mass micro eV, on the order of micro eV. Okay, so in addition to solving the strong CP problem, the QCD axion can also be the dark matter of our universe. And a third motivation that I want to emphasize today is that string theory also predicts axions. So we can accommodate a QCD axion, but also just pseudoscalars which don't have to couple to gluons, so they don't have to solve the strong CP problem. So for all of these reasons, many people have been looking for axions. Here's a slice of those ideas with this really beautiful plot from Karen. So on the x-axis, the mass, and on the y-axis, the coupling strength of axion to photons. So as a reminder, axions couple to photons through this dimension 5 operator here, G gamma gamma A FF tilde, where F is the electromagnetic field strength. And J gamma gamma is inversely proportional to FA with some model dependence arising in the tilde relation there. Now I said that the QCD axion, the mass is inversely proportional to FA. And so in this parameter space, the QCD axion will lie on some band of slope 1, which is this orange band that you see here. So you can see many ideas. Some are based on indirect detection, based on astrophysical and cosmological considerations. And then there's also just direct detection, so laboratory experiments like haloscopes and helioscopes that you can build to look for the axion. And what I think is very exciting is that in the coming decades, if you consider both the current experiments and also future ones, we will have essentially sensitivity to, eight or so orders of magnitude of mass of the QCD axion. So here's just some of those experiments. You have ADMX, which already has sensitivity to the QCD axion band. You'll have dark matter radio, and at even lower masses, dark matter radio gut. And so I think the question that is timely is, where in this parameter space do we expect the QCD axion to lie? So to begin answering that question, let me first talk about field theoretic UV completions of the axion and the cosmology that arises in that case. So what are field theory axions? They are Goldstone bosons of some global U1 Peccei-Quinn symmetry, which is broken at some high scale FA spontaneously. And so let's imagine that we have some complex scalar field phi, whose phase we identify as the axion, and I'll call the modulus of this field S, the radial mode. And let's give phi a potential such that we realize the spontaneous symmetry breaking. So at high temperatures, the VEV of phi will be 0. And at temperatures below the breaking scale, the VEV of phi will be non-zero and parametrically equal to FA. Okay, so really, this Lagrangian is all that I need to tell you in order to tell you the story of post-inflationary dynamics. Of course, this is not the full UV completion. You need other ingredients in the Lagrangian to tell you how the axion couples to the standard model fields. So for example, you can do that by coupling phi to new vector-like fermions, as in the KSVZ UV completion, or you can couple it to Higgs doublets, as in the DFSZ model. But those particular details don't really matter for the story that I want to tell you today. So we just need to remember this Lagrangian here. Okay, and so what happens? What's the early universe cosmology of this Peccei-Quinn field, phi? And the answer to that question depends crucially on when this global U1 symmetry is broken. So it can be broken before inflation, it can be broken after inflation. So what happens if it's broken before inflation? Well, the axion field has some spatial variation, and inflation just selects some patch over which the axion field is initially uniform and blows it up to the size of the observable universe, such that at the end of inflation, the axion field just takes on some homogeneous initial value within our observable universe. So A over FA is just some theta I, some constant angle chosen at random. Okay, and then what happens subsequently is the axion field just acts like a scalar field. It obeys a Klein-Gordon equation. It has a mass, which I mentioned is going to be dependent on temperature. At high temperatures, the mass is 0, and when the temperature approaches lambda QCD, confinement scale of QCD, that mass begins growing. And so morally speaking, the axion is just rolling down some potential. And that field evolution generates an abundance of cold dark matter. So this is the so-called misalignment mechanism. You can compute what that abundance is. It depends on the mass, but crucially, it also depends on this initial angle, theta I, going as the square of theta I. And so if you tell me I want my QCD axion to be all of the dark matter, that does not tell me what the mass is because I don't know what this initial angle theta I is. Okay. On the other hand, you can say theta I is some order 1 angle, and unless there's tuning, it should just be some number which is close to 1. And so in that case, you can still say, if the QCD axion is the dark matter, what the mass is, and it's roughly, you can see from this formula, it's roughly, around 30 micro EV. Okay, so on the other hand, this post-inflationary scenario is more interesting. It will be predictive for the mass. So there, you need the PQ symmetry to break after inflation, right? So the universe must reheat to a temperature which is at least the breaking scale. And in that case, the dynamics of the Peccei-Quinn field are rather complicated. You get these funny field configurations called axion-strings. So these are one-dimensional topological defects of the PQ field, and they're defined by the property that on any contour which encloses one of these one-dimensional strings, the axion has a non-zero winding number. Okay, so if you look at this diagram on the left here, I've drawn some one-dimensional string. I've put some green contour around that. And what I mean is that if you walk 360 degrees around the green contour, the axion field wraps from 0 to 2 pi, some non-zero integer number of times. Okay, so the implication, though, is that if you were to choose your contour to be very small, close to the string, the axion field will be wrapping from 0 to 2 pi in some small spatial region, which means formally, at any point on the string, the axion gradient is diverging. Now, we're talking about, complex scalar field phi, which has continuous evolution. Its derivatives must also be continuous. And so the only way that can happen is if the other component of the field, the modulus of the field, S, the radial mode, is equal to 0 at any point on the string. So the picture to have in mind is that after the temperatures drop below Fa, the radial mode is at its VEV when you're far away from these strings. And then at any point along a string, the radial mode is 0. So there's some interpolation from 0 to roughly Fa. And that interpolation occurs over a characteristic distance, which we call the width of the string, which is of order, it's just 1 over Fa. That's the only dimensionful scale in the problem at this stage. Okay, so what happens? The temperature drops below Fa. You form these axion strings. There's a number of them per Hubble patch, and they're dynamical objects. They're of the size of the horizon. They move around. They emit axions. And while this is happening, the observable universe, the universe is expanding. And so in a given Hubble volume, you can play that again. In a given Hubble volume, you would expect naively that the total length of strings is increasing. Now, on the other hand, these strings, they're emitting axions, so they're actually losing some length due to energy emitted in axions. And what seems to happen empirically, if you do simulations of these dynamics, is that if you wait long enough, these two effects on the string length balance each other out. And so you end up with the regime where the string length per Hubble volume is roughly constant in time. And we call this the scaling regime. And really, it's reflective of the fact that the partial differential equation, which governs the evolution of this field phi, has an attractor solution. So it's the late time dynamics are independent of the initial conditions of the network. Okay, so why do we care about these complicated dynamics, though? We care because these strings, they can emit QCD axions, which eventually become non-relativistic and contribute to the dark matter abundance. In addition, there is still some sort of misalignment contribution here, but it's a little bit different from what I was discussing earlier, because you don't have one angle per Hubble patch. You have sort of a variation of the angle within a given Hubble patch. And so you have to just take the formula for the abundance from misalignment that I showed previously and average over angles. Okay, but this contribution is typically subdominant to the string contribution, to the contribution of from axions emitted by strings. Okay, so let me say a bit more about how the axions are actually emitted from the strings. So what is the energy density per unit time with which these strings are emitted? So this energy emission rate is proportional to the tension of the string, so the energy per unit length. Parametrically, that's just Fa squared, since that's the only dimensionful scale if you consider just some infinite string, straight string in isolation. There's a log factor here involving Hubble. Where does that come from? So if you were to imagine some infinite straight string in isolation and you compute the energy density of that field configuration and integrate it in some disk of radius r, it turns out to be IR divergence. It diverges as log of r. In a real axion string network, there's an effective IR cutoff, which is the interseparation distance between strings, which is of order Hubble. And so that's why you get a Hubble inside of this log. This energy emission rate is also proportional to the total string length per Hubble volume, psi. And then for units, the characteristic timescale over which the evolution is happening is Hubble. So you have a factor of Hubble cubed. Okay, so on the right here, I'm showing some projection from some three-dimensional simulation onto a 2D plane of the axion energy density. And so you can see loops of string. There's a zoom in of a loop of string, which is emitting from some region of high curvature, a classical wave of axion radiation. And so what I care about in the following really is the QCD axions which are emitted. But just as a quick aside, these strings can also emit other things besides QCD axions. For example, they can emit also the heavy radial mode, the other component of the PQ field. And that's actually an interesting story, one which I won't talk about today, but which we looked at with my great collaborators listed here in this paper from a few years ago. And it's interesting because those radial modes can decay into standard model particles, which inject energy into the visible sector, and that can show up in the CMB anisotropy and gamma rays and so on. Okay, so what happens with this string network? So as I mentioned, we enter the scaling regime, and you just wait, and it just persists until the temperature approaches that of the QCD confinement scale, so around 100 MeV or so. And then this potential induced by QCD for the axion becomes active. So what does this potential do to the dynamics? Well, if you look at it, it breaks the U1PQ symmetry explicitly down to a discrete symmetry. And visually, what that does is, if you consider the shape of the potential of the Peccei-Quinn field at high temperatures, it's looking like a sombrero. And once this QCD-induced potential becomes relevant, that sombrero becomes wrinkled, and you now have a number of degenerate minima. The number is given by the periodicity of this cosine, so this domain wall number n. Okay, so the picture to have in mind then is that you have some string, and if the number of degenerate minima is greater than 1, that string will become attached to a number of what we call domain walls, which are 2D topological defects. And you can think of these walls as just separating these degenerate minima spatially. And what happens if the number of domain walls attached to a string is greater than 1 is that that field configuration is actually stable. And that's not good because these domain walls, they carry a tension. You can see they redshift as Hubble. And so if you wait long enough, they will just overclose the energy density of the universe. So cosmologically, that's a problem. So the vanilla version of that scenario is excluded. On the other hand, if the domain wall number is 1, the picture to have in mind is just a loop of string, which is bounded by a domain wall. And the domain wall has a tension. It causes the loop of string to shrink and eventually shrink down to a point. And so that will collapse the whole network of axion strings. Okay, so let me show that with an animation. So here we are looking at the dynamics of the network as the temperature approaches, 100 MeV or so. You see the strings, now you see domain walls, the red things, which become blue. They exert tension of the strings, and the whole network collapses. All of the energy is emitted in axions now. All right. So the statement is that if the domain wall number is 1 and the QCD axion is the dark matter, there's a unique value of the axion mass that gives the correct relic abundance of dark matter. And that statement there in red comes from what I said earlier about the late time dynamics of this network being independent of initial conditions. So the name of the game now is to find what is this value of the mass. And so how do you do it? Well, as I've been alluding to with these animations, you solve the classical equations of motion of the PQ field on the lattice. Okay, so you start with some initial state, you do finite differencing to evolve that state forward in time, and you evolve it into the scaling regime. And then you measure, after you stop your simulation, you measure the axion emission spectrum, so the energy spectrum of axions emitted by strings. And that emission spectrum will allow you to compute a number density of axions that are emitted by the network over the course of its evolution. You can redshift down that number density from the time of collapse until today, and then you can match to the observed dark matter abundance, and working backwards tells you the mass. So that's the basic idea. Several groups have been trying to perform this computation using lattice simulations. And so you can see here from another nice plot from Kjaren what the summary of results from various groups. So you'll see some of these results are accounting for just axions emitted from strings only, and some also account for axions emitted also by the domain walls. But basically, you'll see that all of these mass ranges are different, right? So the answer is all over the place. People generally agree that the mass is tens to 100s of microeV, but no consensus at the moment. So in our latest work from December with my excellent collaborators, Malte Buschmann, Josh Foster, Ben Safdie, what we find is that the QCD axion mass accounting for emission only from the strings is roughly 50 microeV, so bounded between 45 and 65 microeV, which occurs for an FA around 10 to the 11 GeV. If you look at the other mass ranges from previous works, ours is smaller, so we've made progress on that, but that's not the whole story. So I don't want to be too technical in explaining how we've reduced this range, but I want to give you a sense of why this problem is somewhat involved. So what's hard about this problem is that there's a hierarchy of scales here. the strings that have a width of order 1 over Fa, they're evolving on distance scales of order Hubble, and the ratio of Fa over Hubble, by the time of the collapse of the network, it's something like 30 orders of magnitude. So way too large to realize on any computer, even a supercomputer. Um, so what you actually have to do is simulate the dynamics to some point in time where Fa over Hubble is, say, something like 10 orders of magnitude, stop your simulation, measure the axion emission spectrum, and then extrapolate your characterization of that spectrum to the end of the network. So forward in time to the time of collapse of the network. So the name of the game is to simulate as far as you can into the scaling regime. And the way people do that is by simulating on lattices using a static lattice. Of course, you need to resolve the strings. So you want to say something like, I want my lattice to resolve the strings by at least 4 grid sites. And because you do these simulations in co-moving units, the string length in the simulation is decreasing. And so eventually that condition will fail. And so that determines your dynamical range. So you can only simulate so far. What we do differently from the literature is we use a technique called adaptive mesh refinement to simulate further in this ratio of Fa over H. Or another way of parameterizing that is this log of the radial mode mass, Ms over H. And so the idea is basically you have some big grid, say 8,192 cubed sites, and then you refine your grid with 2 times resolution, but only in regions of the simulation volume where you need to do that, in particular where there are large gradients, like near the string locations. So here we're zooming in on a string, and we'll be refining in some location around the string times 2. So you'll have some second level of refinement. You'll have a third level of refinement where we refine again, and so on. You can do that 5 times. And at the lowest level of refinement, the effective grid size of the lattice is there's something like 212,000 effective grid sites, cubed, sorry, 200,000 cubed roughly effective grid sites. Okay, but of course not the full volume is actually refined fully. The strings are moving around as the simulation progresses, so you need to adapt where that mesh is actually refined. And so that's this AMR technique. Okay, so it's very compute intensive. We've run these simulations on the Perlmutter supercomputer at Lawrence Berkeley National Lab, and we used a lot of memory and a lot of compute, something on the order of 25 million CPU hours. Now, let me say what we extract from the simulation to get our estimate of the QCD axion mass. So there's 2 important contributions. The first I mentioned, it's the axion emission from strings during the scaling regime. And to pin that down, you really need good statistics on the emission spectrum, which comes hand in hand with simulating as far as you can into the scaling regime. The other component of the problem is emission during the collapse of the network. So when these walls are forming, these domain walls a priori emit axions in a way which is different from how the strings emit axions. So the strings, they're skinny objects of order 1 over Fa. The domain walls are very different. They're 2D, and they're of width 1 over Ma, so much fatter by comparison. And that second part of the problem is even harder because you have 3 scales which are hierarchically separated, Fa, Hubble, and Ma. Okay, so on the first part of the problem, just to give you some idea of what we do, so we ran some simulation. We ran out to log of the radial mode mass over Hubble equal to 10. This is basically 1 more in log relative to what has been done previously in the literature. By the time of the network collapse, this value of the log is something like 70. So it may seem like advancing by 1 in log is not much, but actually it allows you to refine the estimate of the mass by a significant amount. Okay, so at each point, or at some sampling of times during the simulation, we compute the axion emission spectrum. So for example, we compute the energy density in the axion field. We do a Fourier transform of that to get a spectrum as a function of the wave number k. And then we take time derivatives to get an instantaneous spectrum. So that's what I'm showing in the top panel here. And then what we do is we fit that spectrum to a power law. So we postulate that it's going to be something of the form k over Hubble to the power negative q for some number q. And so we do that fit to that spectral form for some choice of IR cutoff of k and UV cutoff of k. Okay, so we do that at some sampling of times, and then we get some points q, which is what you see in the bottom panel at some different values of the log of the radial mode mass over Hubble. Okay, so what do we find? We find that this our measurement of Q is consistent with a scale invariant spectrum, so consistent with Q equals 1, and this Q being independent of time. So in particular, we measure Q equals 1.01 plus or minus 0.01, so consistent with 1. And we don't find any evidence for this spectral index Q having a time dependence. We have a 1% precision on the spectral index Q, and that gives us, in the end, when you do the computation, this 10% precision on the axion mass. So really, you need to get that value of Q down to a very small error bar in order to pin down the mass. Okay, now how does this compare with previous works? So generally, the previous works from other groups, what they've been seeing is that they're finding evidence for the spectral index Q growing as a function of the log, for example, growing linearly as a function of the log. And what that means is that at late times, when the value of the log is something like 70, this value of Q will be noticeably greater than 1. It could be like 1.2 or something, right? And what that means is that at late times, the axion emission from the network will be IR dominated. Most of the axions are emitted with energy, with momentum of order Hubble. And that just increases the total abundance, and that vastly changes the mass. And so it can push up the mass that you estimate for the QCD for getting the correct relic abundance to much larger values than what you see here. Okay, so there's a bunch of systematics associated with this. I don't really want to go into too much detail. I'll just mention one, which is very important, which is that when you do this power law fit, the UV cutoff is very important. So here I'm showing in the top panel at some fixed time, we've done a power law fit, but I'm varying the UV cutoff, so the largest K, which we include in the fit, and I'm pushing it up to values which are closer and closer to the radial mode mass. And as you do that, the spectral index as a function of time gets a slope, which becomes larger and larger. So you can see that in the bottom panel. And that is precisely the behavior that is reported in some other works. And so what we think, possibly the discrepancy that we're seeing with the other works, is that they've chosen a UV cutoff, which is too close to the radial mode mass, where your dynamics are contaminated possibly by radial mode dynamics. So you care about the axion emission spectrum, but then you have the radial mode dynamics, which are entering if K is too large. Okay, so the other thing we measure from the simulations is the total length of string per Hubble volume, this parameter xi that I mentioned previously. And there, what we're seeing is roughly, if you wait long enough, it just becomes constant, roughly constant. In more detail, it actually grows linearly with the log. And the precise form of this growth, we've compared with the other works. It's actually something that the various simulation groups agree on. So that's very nice. And it tells us really that there's good evidence for an attractor solution at late times. Okay. So combining this measurement of the spectral index, this measurement of the total length of string per Hubble volume, we can compute and estimate analytically what the total abundance of dark matter produced by the network is. And you can see the formula here. I won't explain in detail, but basically FA appears, so you can work backwards to get the correct value of FA. Okay. The other part of the problem is the dynamics during the domain wall, during the QCD phase transition when the domain walls are around. And there we've performed a separate simulation just to study these dynamics as the temperature approaches the confinement scale of QCD. And we have some analytic model for the emission of axions from domain walls bounded by string loops. So we're supposing that our domain walls are circular, bounded by circular strings. We have some formula to calculate the emission, and so on. And we calibrate that analytic model to a simulation. And at the end of the day, what we find is that the domain wall emission may actually dominate over the emission of axions from the strings by a factor of as much as O of 5. So the domain wall emission can actually be the dominant contribution here. And this is not previously appreciated in the literature. What it does is it pushes up the mass prediction to larger values, as large as 300 microeV. So to summarize a bit, we've made progress on reducing the error bar for the axion emission from strings, but now we've sort of reopened this can of worms of the domain wall dynamics being important. Um, and so going forward, it would be nice to understand with better analytic modeling the domain walls better, and then also just be able to simulate further into the scaling regime to pin down the string emission. Unfortunately, that second task requires you just to have more memory, right? To go further in time, you need higher resolution grids, which means more memory. And at the moment, we've maxed out the memory of the Perlmutter supercomputer. So we really cannot go further in time. If I have time at the end, I'd be happy to tell people about some other idea that we're thinking about at the moment to use neural networks to simulate further in time and evade this memory issue. Okay, so that's pretty much all that I wanted to say about the post-inflationary scenario for field theory axions. And now let me say something about string theory axions. So what I'll say is, based on work with my great collaborators, Quentin Bonnefoy, Malte Bushman, Shubhi Kumar, and Ben. And why do we need to talk about string or extra dimensional UV completions of the axion? So the reason is that field theory UV completions have a problem, which is the so-called Peccei-Quinn quality problem. And the problem is that in theories of quantum gravity, you expect, or at least there are arguments for why global symmetries should be violated. So for example, broken or gauged. U1PQ is a global symmetry, and so we expect that it should be broken. It should be violated in some way. Perturbatively, you can break PQ with Planck-suppressed higher dimensional operators of the type shown here. And what such an operator would do is it would shift the minimum of the axion potential away from the value that is needed to cancel the theta bar term. And so if that operator is not sufficiently unimportant, it can spoil the QCD axion solution to strong CP, meaning that the theta bar will not respect this constraint that it should be less than 10 to the minus 10. Okay, so this is actually a pretty serious problem, in my opinion, for field theory axion UV completions. And there's not really that many good solutions. So one solution in field theory that you could say is maybe there's some discrete symmetry, which forbids operators of this type from existing below a certain dimension. But it turns out that if you want FA to be something like 10 to the 11 GeV, as in the post-inflationary scenario, you would need something like a Z11 symmetry or higher. So some discrete symmetry of awkwardly high rank. And that's not very satisfactory. In addition, if you want to have a post-inflationary scenario, so you can actually predict the QCD axion dark matter mass, we know that such a discrete symmetry is in conflict with that because it leads to cosmological problems. In particular, if you had a Z11 symmetry, that would give you a domain wall number of 11. And as I discussed earlier, domain wall number greater than 1 is a problem. Even if you try to model build around that, you still run into cosmological issues, as Matt Rees has pointed out with his collaborators here in a nice paper from a few years ago. Okay, so on the other hand, there's an entirely separate class of UV completions for the axion, which are these extra dimensional UV completions, and they naturally address this PQ quality problem. So how does it work? Well, basically, these extra dimensional axions, they're not Goldstone bosons of a global U1. They are rather zero modes of higher dimensional gauge fields. And let me give an example. So in type 2B string theory, I won't be very technical, but basically you have a 10D theory, right? You have Minkowski space, you have 6 extra dimensions in the form of some compact manifold, X, so that could be a Calabi-Yau manifold. And another ingredient of this theory are higher form gauge fields. So for example, the Ramon P-form gauge fields for higher P, for even P, sorry. And these are just rank P tensors. You can think of them like that. And how will you construct an axion, a zero form? You can construct it by integrating one of these P-form fields on a submanifold of X, of the 6 extra dimensions, which is of dimension P. In particular, you need to integrate it on what's called a P-cycle, which is just a submanifold of dimension P without boundary. And to give you a sense, forget about Calabi-Yaus, just imagine imagine the extra dimensions. There were only 2 of them, and they were compactified in the form of a torus, like I'm showing here. So that's a 2-dimensional object, and you can have 1-dimensional submanifolds, 1 cycles, like this cycle A that I've drawn, and then this cycle B. And these cycles are in some sense independent topologically, because you cannot deform A continuously into B without leaving the surface. Okay, so the claim is that for every independent P cycle, if you integrate a form CP, you'll get an axion. Now, why does this give axions with good quality? Well, basically, these axions have a shift symmetry which descends from the gauge symmetry of this higher form field. And unlike global symmetries, gauge symmetries are protected in quantum gravity. And so naturally, these axions have good Peccei-Quinn quality. That's the rough argument. In reality, there are sources, there's non-perturbative ways that you can break this shift symmetry, but I won't mention them, but we can talk about it later if people want to know. Okay, and the key point here is that for these extra dimensional axions, you can compute properties of them, for example, the axion decay constants, as a function of the geometry of X. So the decay constant will be depending on, for example, the overall volume of these extra dimensions or the volume of particular p cycles, the topology of those extra dimensions, and so on. Now, there's one axion per topologically independent cycle. For some complicated, higher dimensional geometry like a Calabi-Yau, there's many independent cycles of a given dimension. So it's a 6-dimensional volume. There could be many independent 4 cycles, for example. And that's why you get many axions. So this is this notion of the axioverse, which people talk about, which is very interesting. It has a very rich cosmology. Okay. So the question I want to talk about now is what can you expect for the QCD axion mass if you have one of these extra dimensional UV completions? And this is really the question of what is the early universe cosmology of the QCD axion? Do you have a pre-inflationary cosmology where you cannot make a prediction for the mass, assuming it's the dark matter? Or can you have strings, in which case you can make an approximation? And here by strings, I mean axion strings, not the stringy strings, though they are in some cases related. Okay, so this is the question that we looked at in this work. And I just want to give you the result that we find there. What we find is that it's hard to form axion strings for these extra dimensional axion UV completions. The QCD axion dark matter abundance will generically be set by misalignment. And so we cannot make a prediction for the mass just by requiring it to be the dark matter. There are caveats to that conclusion using non-standard inflationary scenarios, which I won't have time to discuss. But those caveats are actually very interesting. They can lead to network dynamics, which are different from the ones that I've presented to you in the field theory case. The reason being that the tension of these strings can be much higher than parametrically FA squared. They can be, for example, something like FA times M Planck. All right, but let me just give you some motivation for the first conclusion here, the question of why we don't actually form axion strings. So the argument basically is that extra dimensional axions, since they're not global, they're not Goldstone bosons of some global U1 symmetry, there is no symmetry breaking phase transition of a U1 as for the field theory axions. So there's no Kibble mechanism which gives you string formation. And this argument was also developed in Matt Reese's paper from last year. All right, so this raises the question of if you want good Peccei-Quinn quality, and so you may think that these extra dimensional UV completions are more compelling in that sense, what can you say about the QCD axion mass? You cannot decide what it is based on requiring it to be the dark matter. On the other hand, there's an additional assumption that you can make about what the standard model does in the UV that will allow you to say something. And so what I want to tell you about now is how if you assume the standard model unifies into a gut at high energies, you can say that the QCD axion mass will be safely below a micro electron volt. So this is work with my great collaborators, Katie Frazier, Mario Reg Lopez, and Ben Safdie. And this came out about a week ago. All right, so the statement is that if the standard model unifies into a gut, as in the minimal supersymmetric standard model, then we'll be able to bound the QCD axion mass between 10 to the minus 8 electron volts and 10 to the minus 11 electron volts. And this bound will be independent of the fraction of dark matter, which is made up by the QCD axion. Okay, so I want to argue now, give you some argument for where this upper bound on the mass comes from. But first, let me tell you what the implication would be. So I'm plotting here on the x-axis the mass, log 10 of the mass. And so the blue band is this mass range prediction. And what you see is that it's completely disjoint from this red band, which is what you would expect for post-inflationary QCD axion dark matter that arises, for example, in the field theory scenario that I discussed. And so what this means is that if ADMX discovers some QCD axion with a mass which is 10 to the minus 4 electron volts, that discovery would be inconsistent with the naive picture of standard model unifying into a gut. And I think it's a non-trivial statement because there's, a good amount of circumstantial evidence for guts, gauge coupling unification, seesaw mechanism, right? Um, okay. The other implication is that at the moment, this blue band is not really probed. You have, on the other hand, future experiments like dark matter radio gut and Casper, which will, at least in principle, get sensitivity down to the QCD axion band. And so that's very exciting. And so this is an additional motivation. Maybe discovery in those experiments can tell us something about guts and or extra dimensions. Okay, so where does this upper bound at MA come from? So here's the basic logic. So suppose that the standard model gauge couplings unify, as in the MSSM, at the SUSY gut scale, roughly 2 times 10 to the 16 GeV. So if you look on this diagram on the right, you have logarithmic runnings of the SU3 color, SU2 left, U1 hypercharge, and they all meet at some point, which is this scale M gut. So if I want that to be my picture, it means that I cannot have any physics below the gut scale which messes with the runnings of these couplings. And if I have a QCD axion coming from an extra dimensional UV completion, there are extra dimensions. So it means that the standard model gauge bosons can, for example, propagate in those extra dimensions and get Kaluza-Klein resonances, so massive resonances coming from quantized momentum in the extra dimensions. And if the mass of those KK modes is below the gut scale, then generically you modify the runnings through threshold corrections, and then this picture of naive MSSM-like gauge coupling unification is ruined. Okay, so what we need to impose then is that the KK masses of these standard model gauge bosons is at least the gut scale, so at least roughly 10 to the 16 GeV. Now, we verified in a number of extra dimensional examples that I will discuss shortly that generally speaking, you cannot push the QCD axion decay constant parametrically below the KK scale. Maybe it can be an order of magnitude or two below, but not much more than that. So combining steps 2 and 3, that implies that the QCD axion decay constant cannot be pushed much below the gut scale. The gut scale is 10 to the 16 GeV, so if you convert that to an upper bound on the QCD axion mass, right? Mass is inversely proportional to Fa. That's something like an upper bound of 10 to the minus 8 electron volts. Okay, so which extra dimensional examples have we looked at for which this bound holds true? Well, the simplest thing you can look at is a 5D orbifold gut. So just take Minkowski space, add an extra dimension in the form of a circle. You actually want that circle to be orbifolded for certain reasons. And whether the metric of the extra dimension is flat or warped, turns out in both cases that we get this mass, upper bound on the mass that I've given. We also looked at heterotic string theory. We looked at axions descending from P-form gauge fields, like I was alluding to earlier. Often you can compute the decay constant analytically under some simplifying assumptions about the geometry of the extra dimensions. And what I want to give you some details on now is the last point here. We've done a numerical scan of roughly 2 million explicit compactifications in type 2b on Calabi-Yau manifolds in what's called the Kreuzer-Skark axiverse. So I'll break that down in a second, but I'll just show you that on this plot we have a histogram, and that histogram comes from a numerical scan of these 2 million compactifications. Okay, so what's this Kreuzer-Skark axiverse? I can't say too much given the time, but basically it's just some class of type 2b compactifications, and it's constructed through a very nice piece of computational geometry, which allows you to map polytopes, so points connected by edges and faces, living in dimension 4, so R4. And there's a whole mathematical machinery which allows you to map a polytope to a Calabi-Yau manifold. There's some finite database of polytopes of dimension 4. And for each one, it's possible now numerically, thanks to the work of Liam McAllister's group at Cornell, to generate Calabi-Yaus from that database. And then for each Calabi-Yau, you can compute, for example, the overall volume, the volume of individual cycles, the topology of the manifold. The software which allows you to do this is a really nice and easy to use software called CY Tools. I had a lot of fun playing with this. Okay, so then how do you get axions from this so-called Kreuzer-Skark axiverse? So one thing you can do is you can say, I have a 6-dimensional Calabi-Yau, and I want to take 4 cycles, so sub-manifolds of dimension 4, and integrate a Ramon-Ramon 4 form over those 4 cycles. That will give you a 0 form axion. The number of axions that you can get like that for a given compactification is set by the number of independent 4 cycles, which for one of these Kreuzer-Skark compactifications is as large as 491. So you can have up to 491 axions. It's a number which it's a very strange number. It comes out of nowhere, but that's apparently what this database gives you. Now, for each one of these compactifications, thanks to these papers here from Liam's group, it's possible to compute for all of the axions in that compactification the relevant properties that you would care about in the 4D axion EFT. So for example, decay constants, masses, axion photon couplings, and so on. And all of this comes from computations using geometric quantities. So for example, here I'm showing on the x-axis the QCD axion mass, and on the y-axis the number of axions. So I've taken, for example, all the compactifications from some subset of 2 million of them, which have 300 axions, and I plot the PDF of the mass. And you see that, the central value of this PDF, it seems to have some correlation with the number of axions. Okay. So what is this? What can we do with the Kreuzer-Skark axiverse in relation to this assumption that the standard model unifies into a gut? Well, let's look on this plot here on the left. So on the y-axis, I have the QCD axion decay constant. On the x-axis, I have the overall volume of the 6 extra dimensions, so of the Calabi-Yau, which is 6-dimensional. And every black point in this plot is a single compactification. So there's 2 million plotted here. There's some relation between the QCD axion decay constant and the overall volume. It scales as some inverse power, 1 over square root of V6. And what can we say then about the Kaluza-Klein scale of the standard model gauge bosons? So looking at this picture on the right, our space-time is Minkowski space, and then this extra 6 dimensions. The QCD axion arises from dimensional reduction of some C4 on this 4 cycle, but that also means that this 4 cycle is associated to the gut gauge group. In particular, the standard model will be living on some brane, a D7 brane, which is wrapping that 4 cycle. And so in plain words, it just means that the standard model gauge bosons are propagating not only in our 4 dimensions, but also in these 4 extra dimensions associated to this cycle. And so that gives them a Kaluza-Klein resonance, which happens to also scale in the same way with the overall volume. So as the volume of the whole manifold increases, this Kaluza-Klein scale is decreasing. And because we need for our MSSM picture of unification to hold that MKK is at least M gut, that imposes an overall upper bound on the 6-dimensional volume V6. So looking back on the plot, so that's this gray band here. And that imposes then a lower bound on FA. So you can see from the plot, the intersection of the gray band with this blob of black points, it's roughly at 10 to the 14 GeV or so. So only, order magnitude or so below the gut scale. Okay. Another acute fact here is that because the overall volume can't be too large in order to have a gut, at least as we're arguing, and there is some correlation between the overall volume and the overall number of axions in a compactification. This result of this requirement of imposing unification into a gut imposes that we cannot have too many axions. So in particular, if you have more than roughly 50 axions, those compactifications are incompatible with this naive unification into a gut. Okay. Now, I realize I've gone a little bit, I've glossed over a lot of the string theory details. And sorry about that. I would like to explain more if I had more time. But as an alternative, let me try to give some argument which doesn't use any string theory at all for why we generally expect this relation that FA can't be pushed parametrically below the KK scale, which is a key step in the logic that I presented earlier. Let me present some argument for why that might hold generally across the string landscape. But I'll give an argument which is bottom up. It only works within it only uses the 4D axion EFT, so it's agnostic to the particular string setup that you have in the UV. And the argument is based on unitarity. So here's how it works. Consider the scattering 2 to 2 of gluons mediated by an axion. Okay. What is the amplitude of that process? The amplitude grows with energy and it's proportional to the Mandelstam variable S over FA squared, right? That amplitude, it's constrained by partial wave unitarity. In particular, it's bounded above by some order 1 number, like 16 pi. And so you get an inequality involving S and FA squared. For the axion EFT, it should be unitary up to the scale, which is the KK scale. So square root of S equals MKK at that scale, it should still be unitary. And so if you plug in this inequality, square root of S equals MKK, you get that FA is bounded below by MKK up to some factors of gauge coupling. Okay, so I think that's a very nice argument. It just tells us that, whether you have heterotic or type 2b or whatever, in all cases, we expect this bound to hold. And just to reiterate, because MKK we're imposing must be at least M gut in order to have naive unification into the MS into a gut. That imposes that FA cannot be much smaller than M gut. Okay. So lastly, let me just wrap up here. So in our paper, we also looked at some caveats to this bound. So one caveat is a situation where you can push FA parametrically below the KK scale. And you can do that in these theories with so-called pseudo-anomalous U1s, where basically the axion arises from the mixing of some higher form gauge field and the phase of a complex scalar field, phi. This was recently worked out in two papers, one by my collaborator Mario and the other by Giovanni Villodoro and friends. And there's another scenario, which is a caveat to our bound, which is that I've imposed that the KK scale should be above the gut scale. But it is possible to accept that the KK scale be below the gut scale, as would happen, for example, as I've alluded to, if you have a very large extra dimensional volume. Can also happen through warping. But there, the worry that you have is a proton decay. So you'll have operators of the type shown here involving 3 quarks and a lepton. And those operators will basically be suppressed by 1 over MKK squared. And so the lower MKK is, the higher the proton decay rate. And unless you do some model building, you're going to violate constraints on proton decay. It is possible, though, through some model building to get around that. All right. I guess I have 1 more minute or so. So maybe let me just say one more thing, which has nothing to do with QCD axions, but which is related to the Kreuzer-Skark axiverse. So we've also searched in the Kreuzer-Skark axiverse for axions, QCD axions, light axions, so ultralight ALPs with masses of order Hubble, which also have very large FA, like larger than roughly 2 times 10 to the 17 GeV. And the reason why we've done that is because there's this recent result from DESI that is claiming there's evidence for evolving dark energy. And one possible interpretation of that is even mentioned in the DESI paper is that you have some ultralight ALP with a mass of order Hubble today, which undergoes misalignment, so with some potential, of the form shown here. And they find that you can actually explain this growing equation of state, omega, from -1 at high redshifts to just something which is growing to be larger than -1 as time goes on, by having this ALP undergo misalignment. And they find that that explanation makes sense if FA is of order 2 times 10 to the 17 GeV or larger. So we've looked, can that be a string axion? And we don't find any axions in the Kreuzer-Skark axiverse which have such large decay constants. And so that tells us that a stringy axion interpretation of the DESI data is perhaps disfavored. Okay, so I think that's really all I wanted to say. Thanks a lot for listening. I hope I've given some general and not too technical overview of what you might expect for the QCD axion mass, depending on cosmology and on UV completion. And I'm very happy to take questions. Thanks a lot.
Thank you very much. Yeah, I have lots of questions, but maybe I will allow other people to go first. So if you have a question, please raise your hand on Zoom or just shout out, whatever you want to do. Yep, you're right.
Yeah, thanks for the talk. Like, I wanted to ask about, I think you showed a plot where you were showing that some Calabi-Yaus cannot solve the strong CP problem, right? So I was going to ask related to this. So the coupling to gluon, so to the GG dual, is it a combination of several actions that you get from the compactification, or how does it work to rule out some of the
Yes.
compactifications? Yeah.
So what this is saying is that there's in addition to, so what are the contributions? So in addition to the QCD axions, QCD instantons, right? There's also stringy instantons like Euclidean D3 branes, which wrap this 4 cycle. And if those guys basically are too large, those instanton scales are too large, I mean, they're generally exponentially suppressed in the volume, right, of the particular cycle to which they're associated. But if they're too large, that will spoil PQ quality.
I see. So in addition, so you're having the axion plus this additional action from the Calabi-Yau, right? In
Yes.
some sense. Okay. Okay. Okay.
Yes.
Thank you.
Anyone else? Okay. Well, regarding this part of the talk, can you remind me again how you get the masses and the GA gammas for the non-QCD axions? You mentioned you have a distribution of FAs, but then when you're referring to this paper by McAllister and others, there's also some way of getting. I mean, I know this isn't the focus of your work, but you will also have masses and GA gammas for those cases. Because I'm sort of curious, where do these axions then end up on the sort of the plot? They with independent of dark matter, are these within reach to high energy astrophysics searches and things like this?
Yeah, great question. It's actually something that we're working on now, basically trying to understand the cosmology of this axiverse in the spirit of Liam's work. So how do you get the masses? So what can give you masses? Gauge instantons can give you masses, like QCD gauge instantons, and also stringy instantons, like these Euclidean D3 branes, which will wrap these 4 cycles. And those masses, you can compute them. They will basically be something, so the instanton scale associated to such an effect will be something like lambda to the 4, and it will be something like m Planck to the 4, and then some exponential suppression. And in the exponents, there will be the volume of the cycle that's being wrapped. So if you have large volumes, those effects should be small, basically. But since we know all the volumes in the of the individual cycles in the Calabi-Yau from this software CY tools, we can compute those masses. As for the photon couplings, so you can compute the photon couplings basically by knowing, let's say there's some axion which is associated to a cycle which hosts QED. So in the case of the gut, this cycle that I've identified, this green thing here, this is hosting the gut gauge group. So it hosts both QCD and QED. And so that axion will couple strongly to electromagnetism. And then the couplings of the other axions will basically be set by mixing. So by kinetic mixing, which is generically weak.
Mm-hmm.
So you can just you can compute the kinetic mixing basically because it comes from the kinetic term of this 4-form gauge field that descends to the kinetic term of the axions, and the kinetic term of this 4-form gauge field, it's a quantity which can be computed as well in terms of cycle sizes and so on. And does that answer your question? Or
yeah, and then I guess regarding the cosmology. Yeah, I guess it's complicated, but do you expect you will end up having kind of one axion, like the lattice axion will dominate the dark matter abundance, if at all, or will it be more of a mixture across the axiverse, or what's your feeling?
Yeah. So So there are situations where often the QCD axion is actually the axion which dominates the dark matter abundance.
Okay.
But there are situations as well where you can have, like, say 10 or so axions which contribute non-negligibly, let's say comparably to the total abundance. But this is a very compactification dependent statement, and one which we're trying to better quantify at the moment.
I mean, you already have enough problems with the simulating the one axion, right? I mean, if it might become a little
one axion.
Yeah, and I guess I know people have discussed this idea of like friendly axions in the case of the axioverse where you have these nearly degenerate mass states. I mean, do you think this is plausible, this scenario, like with all of that added complexity?
Yeah, that definitely happens in this Quasar-Skark axiverse. So basically, the thing, I didn't talk about the masses because it's not it wasn't so relevant for the QCD axion, since you just need to compute the decay constant, right? But generically, what happens in this axiverse, Croiser-Scark axiverse, is that the masses are log flat distributed. And that basically comes because they are exponentially suppressed in the volume. And so the distribution of volumes is, let's say, linear for a given compactification from the smallest volume of some cycle to the largest volume. And so that gives you a log flat distribution. So you'll have like very small masses, like way lighter than Hubble, and then some which are way heavier than the QCD axion. But just by chance, if you have like 491 axions, some will be very close, right? In some compactifications.
Yeah.
And so then the friendly axiverse thing does apply. But the friendly axiverse dynamics, as far as I understand, and I don't want to misrepresent the work of David, but they basically just shift around the energy density between axions, but don't really affect the total energy density. So it's sort of just a redistribution of energy density between Alps and so on, though it does have an effect on detectability. So it's an important thing, I think.
Yeah, maybe I did want to ask a few things about the first part of the talk as well. Yeah, I'm pretty curious to hear what you were talking about using neural networks to get beyond the limitations of current simulations. But maybe I can ask a few more specific things first. So the mesh geometry for the AMR, it looks from your visualizations that it was sort of a cubic lattice, but with just different layers of resolution. Did you how much do you think about the geometry of this mesh? I mean, you know, when people do like finite element simulations, the geometry sort of morphs to sort of reflect the geometry of the thing you're trying to resolve, right? Is it you might imagine for these like
Yeah.
cylindrical objects, maybe there's a sort of some wedge shaped elements would be more efficient, but is that just not worth doing? It's sufficiently added overhead. We're just working out that geometry that it wouldn't be worth doing. I mean, how much control do you have over this mesh in your simulation?
Yeah. Yeah, actually, that we actually wanted to try that. So what we're using a cubic grid here, right? Like subgrids are cubic, everything is cubic. And we're using finite differencing. But you could imagine doing this using finite elements with some different, triangulations or something. Exactly as you said, for the reason you would win for the reason potentially for the reason that you said. But we haven't tried it. It could be, yeah, it could be allowing us to go further in time, maybe, because you would save on memory somehow if you have a more efficient meshing. Yeah.
And also the other thing I'm not I guess you check this when you look at the simulation, but for example, when you have like an axion, a long wavelength axion wave sort of propagating out and it crosses. So you have the higher resolution around the string cores, but then you will have waves which are traversing layers of different resolution. Do you have some way of knowing that you have like correct energy conservation stuff when it passes these sorts of regions? How does this? I don't know how this works necessarily.
Yeah. So I mean, the refinement is not only near the strings; it's also to capture these shocks as well.
Okay.
So yeah. So it's a gradient based refinement. So that is accounted for. Yeah.
Yeah. Okay. Cool. And then I was also thinking maybe I mean you have this analytic model for the domain wall case, and I think you said that you were sort of looking to improve this. I think you mentioned it was like you have like circular strings with a domain wall. I mean, you can kind of see in your simulation that the strings are not really circular, like they have these cusps and stuff.
Yes.
Is
Yes.
this do you expect your sort of this order factor 5 to change very much when I mean do you think it will bring down the uncertainty, but the general kind of qualitative conclusion is going to be the same, that you'll get this sort of boost if you had a kind of more detailed analytic treatment of this case?
So right. So yeah, definitely these are not circles. But we have actually, so this model makes some this analytic model makes some predictions which you can actually confirm with the simulations. And it seems that even though these are definitely not circles, it seems to capture some aspects of what we actually saw in the simulations. Even if that was not the case, I'm pretty sure that this O of 5, it would not be like O of 50 or something because you messed up circles or something. It would be some order 1 effect.
Yeah.
But I should really say, like, we are not 100% confident about this 5 here because we're using analytic models, and also like the simulation is in a very unphysical regime, right? Because of the hierarchy scales is not respected. So yeah, I mean, we are saying that we're not claiming like the axion mass is as large as 300 microeV. We're just saying like this is possibly what could happen based on our poor understanding of these
Mm.
dynamics. Um, yeah. You also had a question about sorry, the neural net.
Yes, please. Yeah, I mean,
Um,
yeah. Let's go to that now because I'm sort of super curious about that because when I naively the sort of situation looks kind of hopeless. Like you want to go to like log of
yeah.
70 or something. It's like, and you're using the best supercomputer in the world and all this stuff. So what's yeah?
Yeah.
Can you go through your ideas here?
So I should say I think this idea probably won't work actually,
Okay.
but
Well, that's okay.
but yeah, but there's it should work in principle, but I think in practice it probably won't work. But basically, what you do is so when you're solving the classical equations of motion by a finite differencing, right? You're solving some PDE equals zero, and what you could do instead is you make a neural network, and the loss function is basically PDE squared, such that what does a neural network do? What is it good at doing? It's good at minimizing the loss. And if you perfectly minimize the loss here, you would be solving PD equals zero. And so what you actually train on, it's basically unsupervised training. So you train on samples of points in space-time, and you just keep feeding points, and the loss just keeps getting minimized. And so, this is not really like classic machine learning. This is like hacking a neural network to use it as a minimizer,
Mm,
essentially. And the reason why this helps with memory is that the only thing which you store in memory are the weights of the network. And neural networks don't really have, that's not much memory in weights. It's like gigabytes or whatever. And so you never store a full box in memory. Now, I've tried to make this work for like a 3D wave equation, this technique. And this technique is related to something that people do in ML called PINs, physics informed neural networks. And they do this and for like fluids and stuff. It generally doesn't work that well, which is like one of the reasons why I'm pessimistic about this. But I have checked that you can do this technique to solve a 3D wave equation, and it is possible. It's just that it takes like a ridiculously long time, so much that it leaves me hopeless
mm,
for the axion-string problem. But I honestly would be very happy if people try this out
mm.
besides us, because it's possible that we're just not doing it properly. Um,
Yeah,
and there's
it's
not
super
many.
interesting.
Yeah,
Yeah, yeah. Yeah, I mean, it certainly seems like the current approach is not necessarily feasible for really going to the physical regime. I mean, you already want to more creatively like this. Yeah, that's
yeah.
super interesting. Um, all right. So I'm aware we've gone on a bit long, but if anyone wants to shout out for last question, just do it right now. Otherwise, I will.